Carpintero, who is full professor at UC3M, and he's gonna talk us about overcoming the challenges of terahertz technology through photonics. So Guillermo should be able to have your role of presenter. Okay.
Can you see it?
Yeah, we can see it. And just a reminder, all of you can leave the questions for Guillermo here in the chat panel, and you don't have to wait until the end of the talk. You can leave them here through the talk, and then we can read them at the end. So thanks very much, Guillermo, and the room is all yours.
Thank you very much. First of all, I would apologize because my title was the only one in Spanish. And when I looked through the other titles, actually I thought that terahertz communications was missing, and I thought I would go back to the initial title that was already mentioned. But I thought that I could focus on the terahertz wireless communications, because it has been one of the drivers for developing terahertz technology. This is my group, and it's the work that I'm going to present is a result of all the efforts together. Not only my group, but also we collaborate with many European colleagues, and in that way we are such a unique group in my university. Now it's 22 years since we started the first project, European project. And the first question is I would like to discuss is why terahertz, and I think this is the main reason why we use terahertz, that is bandwidth, and it's the main reason, and also it's one of the key aspects of terahertz technology. It's all about bandwidth. And bandwidth is actually needed in communications. You actually can see here the frequency bands that are already allocated for wireless communications. Recently in Japan, it's this frequency in 118 gigahertz to 136. But one of the things I can see, these are the current frequencies we use for 5G. Actually, most recent 5G is moving to 1.3 gigahertz, this range of frequencies, below 28 gigahertz carriers, 28 gigahertz. But you can see below, it's the amount of bandwidth that is allocated at these frequency bands. And as you can see, it's quite a small frequency range at the lower frequency, which makes that these frequencies are really congested. And as we move upwards into the millimeter wave and terahertz regions, what you can see is that the figures of a viable bandwidth for communications is just increasing exponentially. And this is really important because if you refer back to Shannon's theorem, actually, if you want to increase the capacity of your channel, it's best to act on the bandwidth than on the signal-to-noise ratio. Okay? And the current allocation of frequencies, the ratio of the bandwidth you can get at higher frequencies is up 50 times what you get at the largest bands in the low frequency. And this is extremely important. Another thing that terahertz is extremely important is because it allows you to generate narrow beams. I mean, for the same size of the antenna. Okay, this is important to mention because in electromagnetics you have the dimensions are always referred to the wavelength, as you can see here, and the beam divergence is relating between the diameter of the antenna and the wavelength of the radiation you want to use. And of course, if you maintain the size of the antenna, as you increase the frequency, the antenna is larger in dimension, and you can reduce the emission beam width. And actually, that means that in the millimeter wave and terahertz, you have these pencil beams. It's narrow beams, which is really important for MIMO systems, and when you want to have spatially separate different users. And this allows to increase the multiplexing in space. This is very important in communications, and also it's very important because you can actually make transmission systems smaller so they can fit them in portable systems. And just to give you an idea of what microwave links were, this is the earliest link that was established in the US. It required 7 towers like this with this size of the antennas that you can see it's even larger than the door you have to use to get into the house where all the equipment is stored. When you move to higher frequencies, actually you can see that the size of the antennas, this I took from a company that makes these antennas in Spain. So I'm proud of this being done in my country, in Anteral. You can see that the sizes are measured in millimeters, and which is really important. Actually, the last advantage is that these frequency bands are being regulated and they are being assigned for communications. And actually, just taking the words of one of the first companies in the US, actually this company, Loea Corporation, was one of that advocated for the use of the E-band for wireless communication and started opening these frequency ranges that it provides peace of mind that the frequencies that you use are going to be used in the future because all the investment that you make stays. Actually, I would like to go quickly with some of the drawbacks, okay, because what I said is, okay, that's great. One of the drawbacks, the main drawback is the losses. Free space propagation loss, the lower the frequency, the higher the frequency, the higher the losses because it spreads the radiation. We can compensate this with the antennas that I just said, reducing the size. And the other is the atmospheric losses where we have peaks of absorption. This is nothing compared to the losses that you get in coaxial cables. I mean, when you increase the frequency, you actually get that the electronic systems, the coaxial cables, which is the most common system to transmit signals, increases its losses outrageously. It cannot be used. And that's the reason why we use rectangular waveguides at high frequencies, but these are extremely narrow banded. And as well as I started with my talk, terahertz has to be associated with wide bandwidth. But as you can see in the current technologies, this is a limitation. This is one of the main problems, and actually this was published in a paper in a IEEE Spectrum, a journal that everyone reads. Actually, this paper did a lot of harm and caused a lot of, when it was published in 2012, we were running a project to generate terahertz with photonic integrated circuits. It did a lot of harm, it was a lot of discussion. And one of the main outcomes of this paper was the problem is the sources. How to generate a source that provides enough power, because we have seen the losses. So that can be compensated with the antennas and of course with the sources that generate it. In communications, all these problems that I just showed you actually has made free space optical communication, FSO, a competing technology with terahertz. It's when you just increase the frequency all the way to the photonic domain. So you are in the hundreds of terahertz frequencies, and the bandwidth, it's usually considered infinite. Okay, compared with the bandwidths that are available in the bands of millimeter wave range. And according to Free's formula, for the same size of the antenna, the received power increases with frequency. And actually, this is one of the main drivers for FSO, because if you combine this increase on the received power with the increase in the photon energy of the optical domain, okay, that means that you can estimate that the signal-to-noise ratio of optical systems is 6 orders of magnitude higher than the signal-to-noise ratio if when you use RF. And of course, these optical systems have, I have to say this because it has been demonstrated and it was a breakthrough. There was a demonstration of optical link with the space from the moon. This was done by NASA in 2013, and in the space sector, they are very much convinced that optical communications are the way to go. But with this, I would like to remember that SNR is not the factor you have to touch when you want to increase the capacity of your channel, because the signal-to-noise ratio is just fitted within this log, and if you do this log in the increase of signal-to-noise ratio, you just get a 21-factor increase. And as I showed you before, if you increase the bandwidth from the low-frequency microwave range to the terahertz range, you just get a factor of 50 just by doing that. So terahertz communications should be considered. You should look at all the aspects, and actually you should see that you can increase. You can get, if your purpose is to increase the capacity of the channel, this is the way to go. Because actually, when you look at this comparison was done by Professor Tadao Nagatsuma in Osaka University. He compared the sensitivity to misalignments of free space optical communication link and a terahertz link. And as you can see, when you change in the x direction of the tilt, this is the angle misalignment, the changes in tilt. You see that the sensitivity of FSO is extremely high. It's just a line compared to terahertz. So this is actually really a key point of terahertz communications. Because actually, if you think about links in space, like landing in ground, you have to go through the different layers, and at the end you have a huge problem with signal scintillation. That means that your beam front is distorted, and you have to resort to extremely costly signal processing to recover your signal, and that is also cost that you pay in energy of running a DSP. In terms of terahertz technologies, there is an electronic approach in which you have VCOs to change the frequency, and then multipliers to increase, to up-convert low frequency into the millimeter and terahertz range. This is done with electronic multipliers. And as you can see, this is the current state of the art. At the end, multipliers, the problem that you have is you have to go through different stages, because actually to get to 12 times multiply, you have to go through multiplying stages, cascade 2 times, 3 times stages. These are narrow band. And this is the bandwidth that you get for tuning. And this is where photonics really comes in place, because photonics is actually, is broadband, as we are aiming to reach with the terahertz technology. So both share the reaching wide bands. It's all about being broadband. We have developed with 35 Lab and UCL. We developed this in 2013. It's a frequency generator for millimeter waves. Is two sources in one single chip. Because of course we want to the wavelength difference is what generates the frequency that we aim to in a photodiode, in a photomixer. And as you can see, the edge where we are now is at developing these sources as photonic integrated circuits to reduce the size, but as well to have the stability of having all the optics involved in generating these frequencies within the same chip. So you don't have optical path length differences that affect the phase. And we have done, this was done by 35 Labs in a dedicated foundry. And we have done, we were able to do this in a commercial foundry at HHI, precisely where Bjorn is located. They have an indium phosphide foundry where you can just send your design of a chip and they will fabricate it for you. And we actually combine two DFB lasers that can be tuned with thermal heaters. This is extremely important because it doesn't affect the optical power, so we get the two wavelengths with the same power, and we beat them on an integrated photodiode. And actually here I can show you that we were able to tune this from 60 gigahertz to 0, but actually the two lasers were actually separated in wavelength 500 gigahertz from starting, and we made them go from 500 to 0 gigahertz. We are looking at some.
Sorry to interrupt, Guillermo. You have 1 minute more or less, 1 minute, 2 minutes?
No problem. Okay, 2 minutes.
Thank you.
Yeah, no problem. We are doing this with optical sources, mode-lock lasers, in which the repetition rate is the frequency that we want to generate, from 100 gigahertz to 1 gigahertz, covering all these frequencies. And as you can see here, we are actually now increasing the power by actually building. You can see here that we have photodiodes, and we are building arrays of photodiodes coupled to antennas to increase the number of emitting elements in phase. And actually, you can see here, this is the power measured with an absolute power meter, and the blue and red is when we have one single element, one photodiode coupled to one antenna, and when we operate them together, we increase the power level that we are emitting. This is the way to overcome the problem of the limited loss in the transmitters. And we have, doing this, we have been able to measure, this is the bit error rate on a wireless transmission link with different sources in the emitting 100 gigahertz carrier frequencies. And as you can see, we are reaching 10 to the minus 8 bit error rate. Finally, this is the work of developing integrated antenna arrays is being done in a European project that we are involving with HHI. It's called Teraway, and it's about not just integrating the signal source, but integrating all the elements that are needed in the transmission to be able to put it into a drone and build this is a hub, a high-frequency hub for communications. And the TerraMeasure, which is the project that I mentioned at the beginning, it's actually to use photonics and electronics to overcome this limited bandwidth of the rectangular waveguides. Because actually, when now you want to characterize a terahertz system, you actually need to resource to these DNA systems using rectangular waveguides. This is where the multipliers are located. This is where the and of course, when you want to change from a frequency band to another, you need to change this head. And having all the multiplier heads to cover all these frequency bands, this costs about €1 million of just infrastructure to be able to measure. And this is not just the only problem. The additional problem is that it's extremely expensive because you have to resource to all these multiplier heads, but it's extremely difficult. As I said, when you increase the frequency, you reduce the size, and actually the probe heads that you need to use to touch contacts in the millimeter and terahertz range, it's extremely difficult. These probes are extremely small, and if you ever see these terahertz probes in a European Microwave Week exhibition, so ask the guy to land the probes, and it will be very difficult. You will have to use your persuasion to get him to land the probes, because very likely every landing reduces the lifetime, if not destroys the probe. Actually, we are developing non-contact systems with photonics, and with this, I just would like to mention, to end with this, that electronics are photonics, are bound to be used together. And thank you very much.
I totally agree with this last sentence, Guillermo. Thank you very much for your talk. I don't see questions here in the chat yet, but as we are super short on time, we extended a bit, like 2-3 minutes. Why don't you leave your email here, your contact details, and I'm sure that if there are some of the attendees that have questions, they can address them directly to you.
Okay, sorry for squeezing the time so tight.
It's all right. It's all right. When we are interested in a talk, we stop. It's fine. Perfect. So thank you very much again for your talk and for your time.